Hello, as part of the Micro and Smart Systems course, today we are going to touch upon another topic that is related to mechanical modeling of microsystems. The topic that we are going to discuss today is related to the residual stress and stress gradients. We discussed in the last lecture what is meant by stress, and now there is a new term called stress gradient. Gradient usually refers to how a certain quantity varies with respect to a spatial dimension. The spatial dimension can be a thickness, width, length, some other quantity. In the spatial coordinates, if you take x, y, z as your coordinate system, how a certain quantity varies with x, y and z, that is called the gradient. That is a derivative of that quantity with respect to that direction, in one direction how that quantity varies. Stress and stress gradients are very important parameters when it comes to the analysis of micro machined components. They are important for macro systems as well, but in macro systems you have stiffness that is very high compared to the stress and stress gradient that exist in them. So, we do not see the effect of that significantly, whereas in micro systems you have components that have very low stiffness and you need to have appropriate adequate stiffness in order to counter for any bad effects that are caused by residual stress and stress gradients. Let us take a very simple example that is shown here, which is a very common example also in microsystems, not only in micro electromechanical systems where there are deformable solids, but also in microelectronic circuits where you need to have interconnects. Interconnects are the elements that connect two different devices. It can be two capacitors, two transistors, two diodes, or diode to transistor, all kinds of connections. They are like wires that we see around in electrical wiring. We have these interconnects. Let us take one of these interconnects that are shown here, this one. So, this particular one is fixed at both ends as it is shown here, and let us say we have applied a voltage potential between these two ends shown by this quantity. Now, when there is a voltage, there will be certain current going through this, and because of the current there will be Joule heating of this interconnect or a beam, if you will. So, it is suspended between 2 points where it is fixed at both ends, and there is a current going through and there is a heat generated because of the current passed through it. It is a very common situation in microelectronic circuitry as well as microelectromechanical systems components. If you have current going through that, it causes heating, and that heat naturally makes its temperature go up. When when the temperature of something goes up, it usually would expand. So, this bar here would want to expand. That expansion is given by a quantity denoted by alpha, which is coefficient of thermal expansion. This gives you the change in length or expansion of a certain material per unit length per unit temperature raise. If this bar, if this interconnect here rises by a temperature T and its length is L, the expansion is given by alpha L times delta T. So, here the L is the length and delta T is change in temperature or temperature rise, change in temperature. So, alpha of course is coefficient of thermal expansion. All materials have certain alpha. some have low thermal expansion, others have very high thermal expansion coefficient. So, these are expansion. So, this interconnect wants to expand, but it is fixed at both the ends. So, it is not allowed to expand. So, what would happen? It would develop a stress, because it is not allowed to move, it will develop a stress, and that stress we can call is a residual stress that is there because it is heated. Okay. As long as it is hot, that stress will remain there. How much is the stress? We have this expansion. I can write the strain, okay, epsilon, which we had denoted in one of the last lectures also. Epsilon is the strain, in this case due to thermal load, because the heating has taken place and it wants to expand, but it is not allowed to expand. So, a thermal strain will get created with a negative sign. So, if I heat it, let us say delta T is positive, then L is positive. L, of course, as we said, is the length of this interconnect. L is positive and delta T is positive, alpha is of course positive for most material. There are some materials which can have negative thermal expansion coefficient, but they are very rare. So, alpha is usually positive, L is positive, delta T, if that is positive, then we have expansion which is positive, that is actually expansion and not contraction. Because it is not allowed, that expansion, the stress created by that has to be opposed. So, we will have a strain which is negative of this quantity. So, strain as we know is change in length, which is negative change in length, alpha L dt delta T divided by the length, which is minus alpha T. So, this will be the strain created here, which will annul or cancel the effect of the expansion. So, it wants to expand, but it cannot. So, it develops a residual stress in the opposite direction. So, expansion effect and the residual stress effect both will cancel, it will remain there. When you cool it, of course, the stress will disappear, then it is not residual stress anymore. For some reason, if it remains there, that can happen in processing due to various reasons, then we call it residual stress. Right now, this is simply thermal strain, and if you want to write thermal stress, we know the stress strain relationship. So, in this case, the thermal stress in this is going to be Young's modulus y times epsilon. So, that will be minus y, epsilon we have just written here as alpha times delta T. So, this should also be delta T, I forgot the delta. So, that is change in temperature. So, we have only cancelled L here, that is alpha delta T, stress is minus Young's modulus times alpha times delta T. Remember that we are using y for Young's modulus, which is the proportionality constant in the stress strain relationship, stress sigma and strain epsilon related by y. So, we get the thermally induced stress. Okay. Now, when it is hot and let us say we lay down another material on top of this, and if that new material and this material have different thermal expansion coefficients, then the stress will remain in both the structures even after they are brought back to the original temperature. So, to see this, let us say we have one layer which has certain expansion coefficient, we top of it put another layer which is has a different thermal expansion coefficient, we join them together, we first raise their temperatures, join them together and cool it. When they are cooled, each of them will cool to different extents. That means that one will contract to a lower length than the other, because they have different thermal expansion coefficients. In those cases, when you bring it back to the original temperature, both of them will retain certain residual stress. So, there are several processing steps where we would have residual stress remaining in the structure. Okay. So, let us take a few more examples. Let us say I take now a beam So, previously what we took the interconnect is also a beam. So, this beam here is fixed at one end. So, this portion is fixed, okay. This portion is free. If I hit this, it will simply expand to by certain amount. So, there is nothing really interesting about this particular thing. It will expand by whatever we derived in the case of interconnect, where we said it will change in length will be related to this alpha times length of this times delta t. On the other hand, let us say we have still have it fixed at this end, and we also have fixed on this entire length. So, this hatching indicates that we have fixed there also. Then what would happen is that it cannot expand here, it cannot expand there, only the top free surfaces can expand. So, you know that whenever we say that it expands or contracts, it is regard to heating, but let us say that the processing of this, that is, we have a substrate, on top of that we have put another layer at a high temperature and now cooled it back to room temperature. The substrate would have certain alpha, and then deposited thin film, a thin layer would have another alpha. So, if the alphas do not match, one wants to contract more than the other when it is brought from high temperature to low temperature. When that happens, let us say that this material has developed a tensile residual stress. That means that to counter that, it has to contract and create a compressive stress and cancel it and become stress free. So, if you look at this portion, the bottom one cannot, because it is fixed to this substrate, whereas the top one that we see here, this top one that can. So, let us see this the mouse, okay, all right, I will just mark. So, this is the top one, and the bottom layer is fixed to the substrate, so it cannot move, whereas the top one can contract, and that is what happens. If you look at the close up view, the top layer is the top edge of this thin film has moved to this point, whereas the bottom one still remains there. So, what you see here is that this surface is actually rotating. When a surface rotates, normally we call something that expands. Let us say you have something here and it expands, that's normal strain or normal stress. When it contracts, that is also normal strain, normal stress, but things can also rotate as we see here, that is called shear strain and accompanying shear stress. Okay. So, the shear strain and stress are different from the normal shear stress, normal stress and normal strain. They are perpendicular or normal to the surface, whereas these are along the surface. The surface itself, there is a force, then it will shear like this. That is what happens in this structure. Let us look at this other quantity, other figure, where the beam is fixed at both ends. It is fixed at this end and it is fixed at this end. Now, when there is a residual stress here, how does that affect the behavior of this system, and that is what we will discuss now. Okay. So, for that what we will do is we will look at that system as shown here. We have certain loading Q of x, okay, and we are taking a small element. Why are we taking this Q of x? You know that from the beam analysis that discussed in one of the earlier lectures, if there were to be a loading Q of x, which is the transverse loading, it is transverse because it is perpendicular or transverse to the axis of the beam, transverse loading. This is a transverse load. When you have the transverse loading, it creates some stress. Now, this Q of x is not any load, we just want to find equivalent transverse loading for the residual stress that may be there in a beam such as this. If I have a beam and if there is a residual stress inside this, if there is a residual stress, let us call that sigma r in it. How do we account for it? What we will do is, let us find equivalent transverse load, equivalent transverse load QR, okay, for sigma r, because we want to see what happens to this beam. Usually when this residual stress is, depending on its sign, when it is positive, then this will be stiffer, that is you have pulled it and kept it in some tension, okay, that is what a positive residual stress would do, and that would make it stiffer. It is like if I take a wire and keep it taut by pulling on it, then you know that it will be stiffer, that is if it were to be slack with a little force it will bend sideways, but if it is very tight, very taut, then if you pluck it, it will be much harder to pluck it, and also the frequency of sound that it generates also will be higher compared to one that is slack as opposed to one that is put in tension. So, that is what happens when it is positive, it becomes stiffer, when it is negative it will become more flexible, to the extent that if residual stress is very high, it could simply buckle. Buckle meaning that you just heat it, that develops a contractile residual stress or negative residual stress, the beam itself might buckle like this. Okay. This is thermal buckling. Thermal buckling. So, the beam itself might just buckle like this. Okay. That is why some of the bridges also collapse when there is this temperature mismatch. Now, when we go to this, we want to find this Q of x or QR that we want to look at, which is equivalent to our thermal residual stress or any other residual stress. In order to see that, we want to get another small concept that we had discussed in one of the last lectures, which is the governing equation of the beam, right. If you recall, y was Young's modulus, I is moment of inertia, and W is the transverse displacement of this, and M is the bending moment. And the sign, negative sign here, because of the sign convention that we have taken, where if there is a moment here, that is positive, if it is on the left side, that is positive. And we also have another quantity called V, which does not appear in this equation right now, but we will see how it comes about, and that is positive on the left side, downwards is positive on the right side. That is because sign convention we get a negative sign here. Now, if I were to differentiate this with respect to x, I would get I want to differentiate this. So, I will get y I d cube w by dx cube equal to minus dm by dx. Okay. That dm by dx is equal to v as it is shown over here. We will derive why that is the case. So, we will get v minus v. So, y I third derivative of the transverse displacement with respect to x is equal to minus of the v, which is called the shear force. So, whenever you take a beam under some loading, if you take a section there will be a force v as it is shown here, that is the shear force, that force that acts in this direction, that is v. If I take a cut here and consider this portion, that would be my v over there as is shown. Now, if I take another derivative, I will have d I y I Young's modulus times moment of inertia d to the 4 w by d x to the 4 is equal to minus dv by dx. This turns out to be the load q that is applied on this q of x that we have taken, that is what it turned out to be. So, in one sense what we have written y I d to the 4 w by d x to the 4 equal to q is our differential equation for the deformation of the beam. This is the main equation. Okay. This for general loading Q of x, that is transverse. Now, as we said, we want to find an equivalent load Q of r, Q sub r, which is the effect of the residual stress that may be in this thing. So, going back to the previous discussion, where we had this sigma r that we want to find, that we are given, we want to find equivalent loading Q r. Okay. So, before that, let us look at these two relationships. Where do they come from? Okay. For that, let us look at actually this itself, okay, this particular diagram. Now, if I take a small element that is shown over here and blow it up as shown here, then there will be a Q of x acting on it in the vertical direction. Let us sum the forces there. This V, we will say positive is upwards, then we have V minus Q dx. Q of x is the force per unit length multiplied by length of this Q dx, and then this is downwards, that is minus V minus dV, or minus of V plus dV. All of them have to sum to 0 for static equilibrium. So, we can cancel the V and V. Okay. So, what we get here is this relationship. So, what we get is Q dx plus dV equal to 0, or dV by dx is equal to negative Q. So, that is what we have here. Okay. Similarly, let us say we take moment about this point and consider moment equilibrium, then we get this relationship. So, we have here, then let us use a different color. Okay. I am going to write now the moment equilibrium. Let us create some space to erase some things. We want to derive this quantity by taking moment equilibrium. Okay. So, let us say counterclockwise is positive, clockwise is negative, then this will be clockwise. So, we will have minus m, and then this is counterclockwise, that will be plus m dm, and this force, since we are taking moment about this point, this will not contribute any moment, whereas this would, and that would be plus V plus dV dx. Okay. In fact, that will be clockwise because the force is downwards, we need to make that change. Okay. This will actually be negative, okay, that is minus V plus dV dx, and so will be the Q. So, the moment due to the Q, the force is Q dx, and then we have to multiply by half of dx because it will act at the midpoint, and this is the dx. So, it will be dx square by 2, that should be equal to 0. Now, when you look at what can be cancelled, this m and m will get cancelled. So, observe what quantities. So, this m and m will get cancelled, we will have dm, and then we will have v dx and dv dx, and then dx square. When there is a quantity dv multiplied by dx, dx itself is small and then dv is also small, product term will be much smaller. So, what we will have to do is we would say that the quantity that multiplies the dx and dx, that will be very small, we can neglect it. So, what we will be left with would be dm by, let us divide throughout by dx, dm by dx minus v, dx dx goes, and then we are dividing by dx here. So, then we will get minus q. This q itself is the force per unit length, as we saw, we neglect this quantity. So, that itself will be equal to 0, implies dm by dx is equal to v. Okay, dm by dx equal to v. So, we have neglected dx square quantity because that is very small, and then we divide by dx, dm by dx, and dv dx also we neglected. So, we get this quantity to be dm by dx equal to v, which is this relationship. Okay. So, having derived this general relationship, now we want to find q related to this equivalent residual stress. Okay. So, for that let us take a little segment which we have denoted here, which has bent because of residual stress. Okay. Let us say that QR that is shown here. So, the QR that you see, there is a little r over there, that is acting on the beam in the transverse direction, and we say that QR causes this residual stress sigma r. Okay. Sigma r multiplied by B and T, where B is the width of the beam, let us say you assume rectangular cross section, and T is the thickness or depth of the beam. Okay. If you multiply them, this becomes area. If you have some other cross section, you simply put area on both sides. Let us say the residual stress right now is uniform throughout the beam, then we have this sigma r times A on the left side and right side, but they will be in the tangential direction, because this is bent because of the residual stress. We are assuming that residual stress will cause it to bend, and we want to find the equivalent loading that causes the bending, that is QR. Okay. Let us say this angle is 2 times phi, this angle here 2 times phi, and this other angle where you take some small element, okay, that angle is from the vertical, that is this is the vertical, this angle is theta. Okay. So, now we want to see how force balance works here, because there is QR acting on it. If we take a small segment, the total force acting on it, okay, and that has to be compensated by the residual stress times area, that is a force and force here, that has to balance, only then this element will be in equilibrium. First, let us look at what happens to the components due to the sigma r. The way the direction is, so this sigma r, if I were to, this direction is like that, if I take a horizontal component and vertical component, horizontal vertical, the two horizontal components get cancelled, whereas the vertical components do not get cancelled, they add up and show up as this. The vertical component, because this angle is 2 phi, this is going to be equal to phi, and likewise if that is phi, this is going to be phi, and you are looking at the vertical component which is a sin phi. So, this is phi. So, this vertical component here will be sigma r sin phi times Bt, two of those, that is the vertical forces, this one plus that is this quantity. Okay. Now, what about how is that compensated? And that is compensated with the QR, that is a transverse loading. So, let us use a different color to make that. So, now we want to see the effect of this QR, that QR2, when I take a force over here and a corresponding force by the same angle over here, there also the horizontal components get cancelled, one goes that way, one goes that way, other goes this way, they get cancelled, only the vertical components will be there. That vertical component is taken as, is shown as QR times cosine theta, the theta is varying, times rho d theta, because QR as you know is the force per unit length. So, you have to multiply by the length, rho here is the radius of curvature, radius of curvature, that is the length, and force, the total force. If you integrate from minus phi to plus phi, the central line is where you have phi equal to 0, this line, and when you have to go from here to here, minus phi to plus phi, that is what is shown here. Then if you integrate it, you will get this, that is what we have equated. So, the vertical upward force should be equal to the downward force. When you do that, then you get QR equal to sin phi gets cancelled, we have Bt sigma r by rho, that is over here, then we get QR equal to Bt sigma r, and then for rho that we have here, we substituted d square w by dx square, because that is the approximation to 1 by rho from geometry. So, this is the curvature. So, curvature 1 by rho is equal to d square w by dx square is what we have used. Rho is radius of curvature, 1 by rho is curvature. Okay, that is a curvature. So, that is what we have here. So, now what we have found is that QR, which is the equivalent transverse load that causes a residual stress sigma r, is given by this quantity. So, if we go back, we had just derived that normal transverse load that may be there on the beam is given by this. Now, we have QR, and that QR, if you say that residual stress sigma r is caused by transverse load, you have to cancel that, that is negative QR. So, we can bring it back this side, because QR is given by this quantity. Okay. So, now we get a differential equation which is yi d to the 4 w by dx to the 4th plus sigma r times bt into d square w by dx square. Earlier we had only the 4th order derivative. Now, we also have a second order derivative term where the sigma r bt is there. So, if somebody says that there is a residual stress in it, you have to put this in. And now, in our derivation we took a small element here. So, we did not make any assumption about stress being uniform throughout the beam. Now, if it were to be changing as well, you can put this sigma r as a function of x. So, the sigma r here can also be a function of x. Residual stress can vary across the axis of the beam, and you can take this into account. This is the new governing equation that we need to solve compared to previous cases where this second term was not existent. Okay. That is effect of residual stress, and whenever there is a residual stress that is positive, then the beam will become stiffer. When it is negative, then it will become more flexible. Okay. Now, what about the stress gradient? You see in this picture that is more than 20 years ago, this is how the micro machined beams look like. On the left side over here, we have let us choose a different color. Here we have some beams which seem to be fine, they are laying flat. These are fixed beams. So, these beams are fixed at both ends, fixed and fixed. Okay. Whereas, these beams are cantilevers. So, they are free on this side, okay, and they are fixed at this end. These beams, as you can see, have curled up, right. Let us switch back to another visible color. See, they all of them have curled up. Why is that? Because they have a stress gradient in the thickness direction. Let us say I take a section of this beam. If I take that beam somewhere there, okay, the stress in this direction varies. If I call that, let us say sigma z, that sigma z is actually varying with the direction. When that happens, when there is a stress gradient, it actually curls up like that. The reason for that can be seen by looking at an example. Let us say that okay, that direction, instead of calling it z, let us call that direction the y direction. Okay. So, when you have the beam which is in this figure, it is fixed here and free there. So, this is the y direction and this is the x direction. Okay. And now, there is a stress that is there inside this which is varying. If I take that stress to be given as follows, it varies with the y direction. Sigma r is equal to, that is the residual stress, sigma naught plus 2 sigma 1 by t times y. Okay. So, sigma naught here refers to the stress that is there at some point, and then when y equal to t by 2, half the thickness, that will become sigma naught plus sigma 1, or when I y equal to negative t by 2 sigma naught minus sigma 1 quantity. Okay. So, at one end it is sigma naught plus sigma 1, other end it is sigma naught minus sigma 1. We can take something like that. So, that is if I have the beam, say the beam, if I start from here, if I say the stress here is sigma naught, okay, and then it increases to a value sigma naught plus sigma 1, because this whole thing is t by 2, if substitute, that will become sigma 1, y equal to t by 2, and then negative it may go to another value which is much smaller. Okay. So, this is sigma naught, this is sigma naught plus sigma 1, this is sigma naught sigma that is sigma naught minus sigma 1. So, this sigma I have to erase. Okay. So, we have stress varying in this manner. When you have that, now what we do is we do the moment balance, that is I take a section here where I know that certain is acting. Now, I take moment about certain point. When I do that, that bending moment at that point will be there, or it causes a bending moment. The effect of residual stress gradient is to bend, and that is what we see here. When there is residual stress, it actually makes this cantilever beam bend or curl as shown here, and that bending moment, equivalent bending moment, can be calculated by take moment of this sigma naught plus 2 sigma 1 by T y, which we have shown here, integrated from minus T by 2 to plus T by 2, that is from here to there. So, this quantity, this level is y equal to minus T by 2, and this level equal to y plus T by 2. Okay, when integrate, you get this as 1 over 6 b t square sigma 1. B is, in this case we are using b to denote the width of the beam or breadth of the beam. Okay, that is the beam width, and we have sigma 1 that is given, and this. Notice that sigma naught itself does not play a role, only the slope of that. If you look at the sigma r as a function of y, this is the slope of that. Sigma naught is this intercept, that does not matter because that is there everywhere, but the gradient is what matters, that is given by this moment. Now, you know that 1 over rho is minus of bending moment divided by Young's modulus times I. This is our Euler-Bernoulli formula. Euler-Bernoulli formula that we had used in one of the earlier lectures also. Now, we substitute for m from here. When you do that and simplify, it will turn out to be 1 over rho, where rho is the radius of curvature, is given by this quantity, or in other words, radius of curvature rho due to the residual stress gradient, radius of curvature equal to rho is going to be equal to reciprocal of this quantity, because we have reciprocal over here, that will be y t by 2 sigma 1. Okay. The more the residual stress gradient, the smaller the radius of curvature. Where radius of curvature is small, that means that it bends more. Note that if there is a straight line, its radius of curvature is infinity, that means that there is no curvature here, there is no bending of this thing, whereas this one has certain radius of curvature. So, it has bent a little bit, but if I take this in this manner, radius of curvature is very small. Look at, in each case this radius of curvature is infinity, okay, whereas this one may be somewhere here. So, this is the radius of curvature, somewhat larger, and here it is very small. So, when radius of curvature is small, that means that curvature is more or bending is more, which is clear. When residual stress gradient is very large, then rho will be small, meaning that it bends more, but if y were to be large, the Young's modulus is very large, then even when residual stress is more, overall quantity may still be large, in which case it may remain flat or bend only a little. So, you can see how it looks like, and if thickness is more, radius of curvature is more, it will resist bending. That is known from your common intuition that when there is a material whose Young's modulus is very high, it resists bending, or when the depth of the beam T here, which we call depth of the beam, that is the thickness or dimension of the beam in the direction of bending, when that is more also, it will not deform much, or radius of curvature is very large, or if it is less, then it will be smaller, it will bend like this. Okay. So, that is the radius of curvature, that is the effect of residual stress gradient, and this residual stress gradient is what is causing these beams to deform as it is shown here. Okay. And now, let us see in microfabrication processes what causes this residual stress. There are a number of them. One we already discussed at the very beginning of this lecture, which is the thermal effects. So, most of the microfabrication processes that happen at a high temperature, they develop certain thermally induced stress. When they are brought back to the lower temperature, this stress remains in them, because different materials that are adhere to each other at high temperatures, when they are brought back to the lower temperature, then we would have the residual stress remaining in them. Other ways that residual stress can get created is because of oxidation, ion implantation, that is when you add certain foreign substances into a substrate or a thin film, then you have residual stress. Imagine how it works. Let us say we take a very naive example of a bus, a city bus. During the peak hours, there are people completely filled in it and more people get in, and as a passenger in that bus, you would feel stress. Similarly, when there are atoms or molecules that are in a substance, if you add more atoms or molecules into them, obviously they feel stress. That is one way to have residual stress. Another is in certain processes such as epitaxial growth, then you are again making them grow in certain places, but then lattice, every atom will have a certain place in the lattice, but if there is a mismatch in the lattice, then there will be a problem. Again we go back to the, let us say, city bus example. There is a seat that can accommodate 3 people. Now a 4th person wants to squeeze in, then all 4 people will feel stress due to their neighbors. So, that is what happens. So, many of the physical or chemical changes that happen in a material would cause residual stress. All of those now can be dealt with in the context of beams by adding this term. Okay. In a general case also similar term will come, and that can be discussed when we come to the general form of elastic deformation equations. Right now we only talked about in the last one of the earlier lectures, and today just discussing just the axial expansion contraction and bending of slender structures such as bars and beams. Okay. So, now we discussed the effect of residual stress and stress gradient. What are the applications of it? It is a bad effect in the sense that it will have some unknown stress which is quite difficult to measure. When you have in a laboratory process some micro machine structure, assessing how much stress there is as a residual stress in it at the end of the processing, when you package and ship the chips, it is difficult to assess. There are methods, expensive equipment is needed in order to measure this residual stress, but what can be done is to throw in a few cantilever beams such as these and how much they rotate. Let us say I have a cantilever beam of certain length and thickness and cross section shape. If I include it there, when I see that at the end of my processing it has curled up like that, based on how much it has curled, which we can measure by measuring this height, and possibly this also may be significant, that is something like this here has become something like that, which will be a circular arc. Okay. By measuring these things you can compute what this rho is, that is the radius of curvature. Know that whenever bending moment is constant, which is what we have here, because Bt and sigma 1 if it is constant in a process stress gradient, then it would cause a constant radius of curvature, okay, that is 1 over rho is equal to all known constants in this expression. So, it will have to bend in the form of a circular arc if you measure the radius of it by measuring this height and this height, this movement of this point in this direction, then we can estimate what the residual stress is. So, this becomes a sensor. So, just add a cantilever into your layout of the micro machine structures based on whether it curves or not. If it does not curve, one can be happy that there is no residual stress in that process that you have done, otherwise by measuring it you can account for it. There are other uses, because if you do not account for residual stress, your calculations will be off, because residual stress does change the stiffness of an elastic structure. You can also use this bad residual stress to your advantage, as has been done by a group in University of California at Los Angeles, where they have made a cage for holding biological cells. Here is a picture of a real micro cage. This is a micro cage for biological cells. These days there is a lot of interest in studying the mechanical or other properties of biological cells in order to single cells that are isolated from the tissues. So, if you take a single cell, you need to capture it. So, in fact, you can see that there is a small object which is can be seen there, that is actually a cell that is trapped. And this one, there are all these fingers, imagine your hand fingers, these are all curled up like this, and when you actuate from below by pressurizing, it will open like the petals of a flower, and the cell comes in and then you can close it. So, this one here, there are all these curled up beams, each of my finger is a cantilever beam that had earlier one had curled, it can also curl. So, all these things are like petals of a flower, and if I pressurize from bottom, I can make it go like this or open up, okay, by changing the direction of the pressure, and when a cell comes in, I can grab it, and that is what you see here. So, there is a use for residual stress. You can actually make cell cages, or one can even imagine putting drugs, medicines in it, and you swallow it, and inside you create that pressure, open it, and the medicine can be released at the right time in the right amount. There are a lot of uses in drug delivery, as it is called. Now, if you notice in this figure, there are some variations. If you look at all of them here, see this one looks a bit darker compared to this, and then there is dark and bright. So, what is that? Why is that there? There is a reason for it. In fact, if I look at any of these beams here that have curled up, so let us say I take this beam that was originally a beam, okay, I have to change the color. So, there is a beam which is fixed here and free here, and the process we have induced the residual stress intentionally, so that it can curl up and become like this, okay, to become the cage. Now, what is done is, if you were to just leave it, it can actually go and become completely closed, residual stress is more, the bending will be more. But the reason for having these bright and dark portions is that what they have done is taken a beam and they have put this stiffeners in some place. Okay. So, whatever has curled up which has this stiffener is looking a little bit darker compared to the other one which is slightly brighter. So, that they have added these ribs on top of the beam. Why did they add? For that we need to understand an effect that we have not yet talked about, which you are probably familiar with earlier, called Poisson effect. What is Poisson effect? If I take a bar, we always start with a simple example of a bar of length L, and I have elongated to new length L prime. Okay. Then what will happen is that in the other dimensions, in the x direction we have elongated, in the y and z direction it gets contracted, that is the Poisson effect. Okay. X direction we have elongation and that causes contraction in the z and y direction. So, y direction and z direction it causes contraction. This is common knowledge. If you take a rubber band and stretch it, rubber band becomes thin, that is the Poisson effect. And this has a lot of implications, especially in this particular example. What happens is that if there is a residual stress gradient causes it to curl like that, perpendicular to this direction, that is here, it will curl the other way. So, when my finger, let us say, curls up in this manner, so observe that it curls up in this manner. If I were to look at this quantity, that will curl up like this. If I were to magnify this, it will curl up like this. So, one is going like this, other would go the other way. Let us look at that in the form of a figure. If the beam is bending as shown here in this direction, in the cross section direction it will go the other way. So, let us look at the figure now. So, where we have on the screen a little element that is shown, where we have this bending in this manner, this other one will bend in this manner, creating a saddle surface like in a horse saddle, and this is the effect of the residual strain and the Poisson effect. Poisson effect is, I just said that if there is elongation in one direction, in the perpendicular direction there will be contraction. Okay. So, if there is a sigma x in the x direction, in the other directions also there will be a sigma y, which is negative of sigma x times a ratio called Poisson ratio. Okay. Likewise, there will also be an epsilon z, which is negative of this and then x. Okay. So, if I were to have this effect and to prevent this from becoming a tube. Now, if you see this bends like this, other way it goes bends the other way. So, what will happen is this will actually become, if you were to imagine this like a tube, and this tube bending is what you will see. Then it will not act like a cage. Each of my fingers that we saw earlier become like tubes or thin wires with a hollow section. So, it will not be effective as a cage, and that is why they have put these. Okay. In order to model such as these and how to understand what they mean, we need to look at the all mechanical effects, and one of them is this Poisson effect. This Poisson effect, while we are at it, let us discuss another very short concept, very small concept of how materials are compressible or not, that is contained in this Poisson's ratio. If I look at this bar, what is the change in volume of this? The change in volume is given by this quantity. How do we do that? Now, I have written the strain in the x direction and y direction and z direction, and if I look at the total volume of the new one and the old one, if I take the difference approximately, if I neglect the higher order effects, then it will be the volume Lx, Ly, Lz, length in the x direction, length in the y direction, length in the z direction, that is the original volume V. Now, new volume is 1 minus 2 nu epsilon x, that comes because these other strains that are created. You need to calculate this delta V as the original volume of the thing, which is this, minus the new volume of the dashed line structure, you get this. Now, if you take the ratio of delta V by V, that will be given by 1 minus 2 nu into 1 over y. Okay. Here what we have done is we have taken the strain. So, now strain okay, we have the strain epsilon x is equal to the stress, that is sigma x divided by Young's modulus. The sigma s we can also replace by Px by y. Okay. That is why we have all this quantity. It is nothing but just epsilon x divided by y, and sigma is replaced with pressure, because after all stress is force per unit area and so is pressure. That is what we have done here. So, when you do this, delta V by V is 1 minus 2 nu into pressure in the x, y, z directions, because we have taken only x direction. Now, if it happens in the y and z directions, we get this quantity, and there are 3 of these pressures. If they are all equal, which we call hydrostatic pressure. So, when you put something in water or any liquid for that matter, the pressure in the x, y and z direction will be equal, then we will get delta V by V 3 times of that pressure this. Now, we can define a new quantity which we will call the bulk modulus, okay, which gives you relative change in volume, okay, for the applied pressure. So, bulk modulus is how much pressure is needed for a unit relative change in the volume of the material, and you can see that is given by this quantity, Young's modulus divided by 3 times 1 minus 2 nu. Whenever nu is equal to 0.5, this becomes 1, 1 minus 1 0, in which case k becomes infinity. That means that such a material would have delta V by V, because now that becomes infinity or this is 0, that cannot be compressed. So, when nu equal to 0.5, that material will be incompressible, whereas if it is more than 0.5 sorry less than 0.5, 0.2, 0.3, which is for most metals, and for silicon also you can take it as 0.25, 0.25 to 0.3, then it will be slightly compressible. So, we learnt another concept which is related to Poisson effect, and we apply that Poisson effect to call what is called anticlastic curvature. When beam bends in one direction, it will bend in the cross section direction in a other way to create a saddle surface, and that is also used to make the cages such as the one shown here. Okay. Let us summarize what we have discussed today. We discussed what causes residual stress, thermal processes being one, but there are a lot of other processes where extra atoms are introduced into the material, and that not only the stress gradient is also important. So, in fact, we should note that the stress may not be uniform throughout the structure, and it can even be different in different directions. We can account for that using modeling, whereas we have discussed only in this lecture in bars and beams, which make up most of the micro machine structures. And we have discussed the Poisson effect and how residual stress and residual stress gradient can be used for our advantage. In the next lecture, we discuss some more concepts of modeling. Thank you.